In today's lecture, we will discuss a problem related with the stresses in composite bar. What do you mean by composite bar? Suppose we are having a structure like this. Suppose we are having two bars and loads are hang like this. So this load is carried by both the bars, maybe two or three or four or something like that. Maybe some other kind of uh, configuration of that bars are there. In this way we can say uh, we can apply a load like this, or by some other ways also we can apply the load. So these are the called the composite bars. So how the stresses are generated, how this load is carried by these members, so we will explain it with the help of a numerical problem. Let us see. The two vertical rods of steel and copper are firmly secured at their upper ends and lie at a distance of 100 centimeter apart. Suppose we are having a roof and on it there are two bars. One is having steel, another is having copper. Same cross sectional area and same length. Each 3 meter long and of 30 mm in diameter. Cross sectional area and uh, length is same. This is steel rod and this is copper. A horizontal rigid crossbar connects the lower ends of the rod, and on it a load of 40 kilonewton is placed. Suppose we are having a crossbar like this and a load is placed on this crossbar. So these are 100 centimeter apart. 100 centimeter or 100 mm. 100 centimeter, no, it is 100, say 100 mm apart. This is 100, all dimensions are in mm. This is 100 mm apart. So now there are two conditions. We have to find out the location of load on the crossbar if it remains horizontal after being loaded. What does it mean? If it remains horizontal means what? The strain in both the members should be same, then only it will be remain horizontal after the extension. So let us start this solution. Very first thing, the cross section diameter is given here. Length of the rods are 3 meter and its cross section is given as 30 mm in diameter. So cross section of steel as well as cross section of copper can be calculated by pi by 4 d square. 30 mm square d square, that will be in mm square. By solving it, we will have a value 706.5. 706.5 mm square. Keep it in mind. Now we'll start the first part, location of the load on the crossbar, so that if remains horizontal. Suppose it is located at a distance, say this is the this is the crossbar, here is the load, we can draw the forces on this crossbar. Say this is force due to, because in the steel bar, and this is force, not load, in the copper bar. Suppose we are applying a total load P, that is 40 kilonewton, 40 into 10 to the power 4 newton at a distance say x from here. So what is the initial thing? The total load P will be equal to load on steel plus load on copper rod. First thing. Second thing, elongation del L of steel should be equal to del L of copper to meet the first condition, that remains horizontal after being loaded. It is only possible when elongation in both the rods will be equal to. Del L of copper should be equal to del L of steel. Right. Now from here we can say that del L is equal to what? Del L is equal to PL over AE, or in more simple way we can say that strain instead of writing this, we can say, because initial length is same, so we can write strain in steel should be equal to strain in copper, and strain is your stress by area. Sorry, stress by E. So that is equal to stress in copper by modulus of elasticity of copper. So from here we can get a relationship. Sigma S is equal to sigma C into ES by EC. ES by EC, we can see the relationship. ES by EC come out to be 2, means it will be twice of sigma C. Sigma steel is equal to twice of sigma copper. This is first thing. Another is this one and second. From one we can write that, see here, from first, total load, that is 40 kilonewton. 40 into 10 to the power 3. From equation 1 we can write here, from equation 1 we can say total load, that will be equal to load because of steel, and load is steel is equal to sigma steel into area of steel plus sigma copper into area of copper. From here we can write sigma S. Sigma steel is twice the sigma copper from equation 2 into AS plus sigma C AC. AC and AS both are equal. So from here AC and AS both are equal. So we can write 3 sigma C into AC. AC is here the value of 706.5. So from here we can calculate the value of sigma C, and it will come out to be 18.872 Newton per mm square. By putting this value in equation 2, we will have the value of sigma S, that is stress in steel, and that will be equal to 37.744 Newton per mm square. So by these we can calculate the load carried by or shared by steel rod. That will be equal to PS is sigma S AS. So we can write here 37 point this into AS is your 706.5 mm square. By putting these value we can have a total value 26667 Newton on steel, and load carried by copper rod will be equal to sigma C AC. Its value will be 13333 Newton. So by these, now see the forces acting on that crossbar. PS will be equal and opposite to that which is acting on the steel rod. PC is like that. So if we write the moment about the, say this is point A, this is point B, this is point C. If we are writing the moment about A, moment will be 0 because it remains horizontal, it's shifted horizontally downward. So moment about A will be 0. That we can write that P is PC multiplied by this distance, that is 100. PC multiplied by 100 will be equal to 40 into 10 to the power 3 multiplied by X. So you can see that value of PC is 13333 into 100 divided by 40 into 10 to the power 3 is the value of X, and it will come out to be 33.33 mm. So location of X can be location of this load can be calculated in this way. The second condition in this problem is what will be the inclination of the crossbar if the load is hang at its mid-span. The second case, that we are not putting it at a distance X, but we are putting it in the midway, means 50 mm from here. So in this condition we can say that load is shared equally by both the rods. If it is 40 into 10 to the power 3 and this is say 50 and again this is 50 mm. So this PS is equal to 20 into 10 to the power 3, and that will be equal to PC. Both the load taken by both the rod will be equal because it is hang exactly at the mid span. In that case, we can see that elongation in rods will be different. Definitely one will elongate more as compared to others. Suppose we are making a drawing again. This is the initial condition, and after loading, suppose it elongate till this one, and suppose it elongates like this. So the location of crossbar will be something like that. We have to calculate this inclination theta. We can clearly see that the value of this is your del L steel. If it is steel bar, the elongation in steel is this much, and the total one is del L copper. So this will be del L copper minus del L steel. Elongation of copper rod minus elongation of steel. Right. So now in this triangle, we can calculate this angle tan theta by del L C minus del L S upon 100, that is base. So the whole thing reduces to calculate the elongations in both the bars. We can calculate the elongation, say del L steel by PL over AE. The value of P is 20 into 10 to the power 3. L is 3 meter, convert it into mm, 3 into 10 to the power 3 mm upon A. We have already calculated the value of A, 706.5 mm square, 706.5 mm square, and E is given for steel 2 into 10 to the power 5. So from here we will have a value of del L steel as 0.4245 mm. Similarly, we can calculate the value of copper, del L copper, by the same expression, 20 into 10 to the power 3, 20 into 10 to the power 3 multiplied by 3 into 10 to the power 3. PL upon A is also same, but E differs. It is 1 into 10 to the power 5 instead of 2. Here it is 1. So its value come out to be 0.849 del C, 0.849 mm. By putting these values in the equation of tan theta, will have a value of theta is equal to 0.24 degree, 0.24 degree. So in this way we can calculate, we can solve the problems related with the stresses in composite bar. Thank you.